light, it's going to manifest physically more like a wave. If you have shorter wavelength light, it's going to manifest physically as more like a particle. Okay? So one can produce interference and diffraction effects using prisms and lenses with light. Moreover, Maxwell had shown that light was actually described mathematically by an equation called the wave equation. The wave nature of light is therefore predicted by this theory. So pretty much Maxwell's equations or the E&M, those are all considered classical theories, and it treats light like a wave, okay? On the other hand, Max Planck's work, so Max Planck is a contributor to quantum mechanics. So that work on the radiation emitted by hot bodies had also shown that light could also behave as if it came in discrete packets, which he called quanta. So there we go, light having a wave nature as well as a quantum or particle nature. He hesitated to claim that these quanta could be identified with particles. It was in fact Albert Einstein in the work on the photoelectric effect, for which he won the Nobel Prize, who made the step of saying that light was actually made of particles. So Einstein is therefore called a father of the old quantum mechanics, which deals with sort of this quantum nature of light. So Max Planck may have been the one to have found these discrete packets coming out of the radiation from hot bodies, but it was Einstein that actually gave us the photoelectric effect, and that is what he won his Nobel Prize for. Even though he's more famous for his relativity work, relativity was not really understood very well back then enough for people to have confidence giving him the Nobel Prize for that, okay? So they instead gave it to him for the photoelectric effect. So if you discover something or invent or innovate something extremely out of this world, amazing, and takes a lot of intelligence, maybe also discover some other thing too, and you might just get the Nobel Prize for the lesser discovery, if you will. Not that photoelectric effect is anything small. These particles later became known as photons, but how can something be both a wave and a particle? One has to say that reality cannot be exactly described by either concept, but that it behaves sometimes as if it were a wave and sometimes as if it were a particle. And I was just telling you sort of the manifestation and the trick to understanding when light will be a wave versus when light will be a particle. Longer wavelength light will manifest more like a wave. Shorter wavelength light will manifest more like a particle in your physical experiences, okay? Imagine a medieval monk returning to his monastery after his first trip to Africa. During his travels, he chanced upon a rhinoceros and is faced with the task of describing it to his incredulous brothers. Since none of them has ever seen anything as strange as a rhino in the flesh, he has to proceed by analogy. The rhinoceros, he says, is in some respects like a dragon, and in others like a unicorn. The brothers then have a reasonable picture of what the beast looks like. But neither dragons nor unicorns exist in nature, while the rhinoceros does. That's the duality of a rhinoceros, sort of a unicorn, sort of a dragon. It is the same with our quantum world. Reality is described neither by idealized waves nor by idealized particles. So don't idealize waves or particles. That is not reality, okay? But these concepts can give some impression of certain aspects of the way things really are. The idea that energy came in discrete packets or quanta was also successfully applied to the simplest of all atoms, the hydrogen atom, by Niels Bohr. So again, huge contribution generally in the 20th century to quantum mechanics came in the form of stuff with the hydrogen atom. And that was done by Niels Bohr, really cool guy. And oh, thank you so much. Thank you, Julian. Thank you, Eversor, and thank you, Chickpea. Thank you, everybody, for being here. So the hydrogen atom in the 20th century by Niels Bohr and all of his work in the 20th century led to other aspects of atomic and nuclear physics. The existence of discrete energy levels in atoms and molecules is fundamental to the field of spectroscopy